Good afternoon, everyone, and welcome to this latest in a series of webinars by the IMechE on the energy transition and where our opportunities and barriers are for the transition to net zero. I'm going to talk to you today about geothermal energy, and I'm going to do so as something of a passionate advocate for it in my role as CTO of IMechE Energy Technology. IMechE is developing a new generation of drilling equipment which will drill accurate wells at very high temperatures and enable some of the wells that you'll see in the presentation later on, which are designed for the generation of electrical power. Now, I made a presentation to IMechE on geothermal energy earlier in the year. I'm not going to repeat the whole of that presentation, but just to recap a few points, we've been using geothermal energy for a long time. This is an image of the Roman baths in Bath Spa in Somerset in England. And these baths have been in operation pretty much consistently for 2,000 years, providing hot water, which is taken directly from the ground. Less than 120 years ago, we developed our first electricity generation from geothermal energy. This was at Larderello in Italy. This is a picture of the site as it exists today. And that shows the potential of geothermal, not just for heating and cooling, but also for high power electricity generation. Talk about both of those opportunities during the course of this presentation. I used to be skeptical about geothermal energy. Iceland and volcanoes are very much in the news at the time of this talk. I used to think about geothermal being associated just with tectonic activity and just with areas where there was heat very close to the surface, places like New Zealand, Indonesia, and of course Iceland. I've been disabused of that theory, and I'll show you some of the reasons why in a few minutes. But this is a typical geothermal power station in Iceland, and it uses steam from hot water or multi-phase reservoirs under the ground to generate electricity, just like a coal-fired power station or a nuclear power station would use steam to generate electricity. Now, in geothermal, there's quite a broad spread of applications. You can use it directly for heating and, as we'll see in a few minutes, for cooling, residential and industrial applications. And there you don't need too much temperature. You don't need to go very deep underground. Something between 30 and 40 degrees Celsius can be enough to provide heating and cooling for residential buildings, industrial buildings. Hydrothermal wells go for natural resources where there is already water or steam or multi-phase present in the rock. Places like Iceland, California is big at this. Hydrothermal provided 6% of California's electricity in 2020. But demand for it is growing faster than hydrothermal capabilities. And it is only found in those unique parts of the world that I talked about a few minutes ago, places like Iceland, New Zealand, Turkey, Italy, places which are fortunate in terms of their tectonic activity. But you can also build artificial geothermal reservoirs, and there are a couple of ways of doing that. Enhanced and advanced geothermal systems both will generate steam or perhaps steam-like fluid from a different liquid. Both of them use turbines on the surface. Both of them are capable of generating electricity, and both of them can do so in hot, dry rocks. That is, they can do so in places where you don't need to have fractured rocks with water in, and you don't need them to be in places where there is heat very close to the surface. You just have to drill a bit deeper. This shows in a slightly more illustrative way what I've just been describing, and you can see that technical complexity and the amount of power generated increases from left to right as you go across this graph, as does depth and as does temperature. Open loop heating and cooling can be done with very low temperatures, very close to the surface. Hydrothermal systems and EGS and AGS systems, much deeper and much hotter, and can be a lot deeper and a lot hotter than is shown on this simple diagram. If you get down close to 400 Celsius, for example, you get into supercritical steam, which gives you a whole step change in the amount of power that can be generated. This is just a simple way of showing us that we're going to need a lot of electricity. There's a couple of Sankey diagrams here. This one is showing current global energy flows. And you can see that electricity is relatively small in this compared with the growth in electricity, which is shown in yellow, by the way, by 2050, which according to the IEE's net zero scenario is going to more than double in terms of its scale and significantly increase in terms of its importance to the global power network. It's going to become the biggest energy vector by 2050. So we're going to need a lot of electricity. And how do we get it? Well, there are various ways of getting it. They're shown on this curve, and you see that the technologies on the right are kind of non-renewable resources. Nuclear is included in there, but you also see natural gas, oil, and coal. And you can see that they have significant greenhouse gas emissions at source as the power is generated. On the left-hand side, you can see renewables, bio, solar, wind, and of course geothermal's in there as well. And you can see that all of those, including geothermal, have very low GHG emissions. So geothermal gives us the potential for low GHG electricity generation, which maybe makes it part of the energy picture going forward. But then we look at capacity, and by capacity, we mean the amount of time that a particular energy source is available for. And we all hear arguments about wind, particularly onshore wind. It's only available when the wind blows, and solar is only available during the daytime, which is slightly more predictable. So you can kind of manage that a little bit more. But basically, they all have relatively low capacity. The renewable resource with the highest capacity is geothermal, because the heat is always there underground. Not only that, but it's also very controllable, which means that it can be, the amount of power generated can be switched on or turned down relatively quickly. And that combination of controllability and capacity makes it very useful for balancing a grid. And if we don't have something like geothermal to balance the grid, we're going to carry on burning natural gas, because we need a way of switching power generation on and off fairly quickly to match consumption. And this data is from Geothermal Canada, but these numbers are pretty much universally applicable. They're not going to change very significantly going from country to country. The capacity is really a function of the nature of the power generation process. The other issue that you can get with some renewables is grid congestion. And grid congestion, it's kind of exactly like it sounds. It basically means that you have power going into the grid from a power source and power being taken from the grid by a consumer or by a user. And the transmission network is not capable of accommodating all of the transactions necessary to get the power from the source to the user. That can become a problem with some renewable energies if they have to be placed remote from the point of use. And offshore wind is maybe an example of this. I lived in Texas for a number of years, and one of the things that characterizes Texas is that in the north and the west, there's a lot of capability for wind power generation, and there's a huge amount of wind turbines. And then all the people live in the south and the east. And so then you have to get all that power from the northwest to the southeast. And unless you have an infinitely large grid, which is obviously prohibitively expensive, that can be difficult to do. One of the things about geothermal is that it's relatively agnostic to where you place it. So you can choose to place geothermal installations if you're creating artificial reservoirs close to population centers or to industrial centers, and therefore reduce the amount of grid usage that you need. Or, and I think I covered this in the talk earlier in the year, you can choose to place geothermal installations where you have decommissioned, say, coal-fired power stations. And so then you can leverage the existing grid capability which is in place. You know, once you've decommissioned a power station, you've still got a load of transmission lines coming in. So what better way to use them? This is an example of an enhanced geothermal system. It's a very, very simplified model, but an enhanced geothermal system creates its own permeability by drilling multiple wells. There's two shown here, and then creating artificial fractures between them, using a technique which is not identical to, but which is similar to the techniques used to fracture rocks in unconventional oil and gas. And by fracturing, you create a network of subterranean fractures. You pump cold fluid into one of the wells, and you retrieve hot fluid from other wells. For many years, this was a technology that people had tried, and you heard this. Well, we tried this before, and it didn't work. And I'll show you an example in a minute of how it was actually made to work. There's also advanced geothermal systems, which is another system that can be drilled into hot, dry rocks. There's a variety of potential well designs shown here. The one on the left is like a downhole radiator, very complex well with multiple branches which connect at the end. One thing I will say is the oil and gas industry knows how to drill wells like this. It's just a question of temperature, and it's just a question of being able to drill them at high enough temperatures. But all of the drilling technology that we need to do this sort of stuff, with the exception of temperature, exists, and I'll come back to that towards the end of the talk. The UK is starting to look at geothermal energy for heat, which is really good. Swaffham Prior, which is in Cambridge, has actually got like a community ground source heating system for heating people's homes during the winter months. 108 boreholes capable of delivering 300 homes with heat delivered at 72 degrees Celsius, which is going to be more than capable of heating people's homes to the sort of 18 to 20 degrees that we find comfortable. And closer to where I am, I'm sat in Cheltenham, Gloucestershire today. Celsius Energy is developing these pyramid-shaped geothermal exchanges, drilling wells down to about 200 meters, but drilling wells which are close to vertical, so they don't have a very big land use footprint, and using those for both heating in the winter and cooling in the summer, and using the relatively stable temperature underground to achieve both of those things. So saving energy on maybe gas-fired heating in the summer, and saving the use of electricity for gas-fired in the winter, and saving the use of electricity for air conditioning in the summer. But I mentioned EGS a few minutes ago, and this is a real well that was drilled by a real company, Fervo Energy in Nevada earlier this year. And they drilled down to about 7,700 feet, and then drilled a 3,200 foot horizontal well. Very, very simple well design when you think about what the oil and gas industry is capable of doing. And they managed to make EGS work. And they did a few things that were different from the way that people have tried to make EGS work in the past. They had a monitor well. You can see the vertical well there to the right of the two primary wells to understand what was going on. And they drilled one horizontal well, and then they did a hydraulic fracture. And they did a lot of measurement of the parameters while they were fracturing, and a lot of modeling of where the fractures went. And they also did a multi-stage fracture. A lot of EGS in the past might have tried to do one or two stages of fracture. Fervo did something a little bit more akin to what unconventional oil and gas wells might do, and they had 102 stages, I think, in their fracturing process. And as a result of the care they took over the fracturing and the modeling and the measurements that they did, they had a pretty clear idea of where the fractures had gone. And so they drilled the second well to intersect the fractures. They did this at up to about 190 degrees Celsius, so able to use existing oil and gas equipment, kind of on the limits of it, but able to use it. And they were able to produce 3.5 megawatts. 3.5 megawatts isn't huge, but it's a lot bigger than the 0 that had been achieved before. And it's just a first step. It's like a baby step. And I believe they have a project ongoing now, which they expect to deliver about 10 megawatts, and it's just going to grow from there. So this has proved that we can actually get electrical power from hot, dry rocks with all the benefits that I talked about before. So high capacity, high availability, high controllability, and very low greenhouse gases. So this is almost like a vision of the future, if you like. And unconventional geothermal wells could look very much like unconventional hydrocarbon wells in North America. The image here is actually an oil or gas installation with a number of pads, and from those pads we have a number of horizontal wells. And you can see the blurring around them is hydraulic fracturing. In the case of the oil and gas wells, you don't want the fracks to intersect each other, and so they're distinct. In the case of EGS wells, you will actually want them to intersect. So it looks slightly different, but many of the technologies will be the same. And pretty much all of the pioneering companies in this industry are talking about the use of horizontal wells. And we know how to drill horizontal wells. Like I said, it's just a question of drilling a bit deeper and a bit hotter. But my company, Hefe, is one of a number of companies that's working to enable the increase in temperature capabilities of various pieces of equipment. And if you talk to the US Department of Energy, they're very bullish about it. If you look on the US DOE's page, they have 5 things done about geothermal power. One of the things that hits you right up front as you look at their page is that they're predicting that geothermal could meet more than 10% of US electricity demand. And if you could scale that globally, if geothermal could hit 10% of global power demand, that'd be a lot of geothermal wells to drill, and I'll come back to why that's a good thing later on. But that's also a lot of emissions taken away and a lot of controllability put on the grid. So it all sounds great. The title of the talk included talking about suggested we're going to talk about barriers. So where are the barriers? And there's a couple of barriers, really. One of them is what people's view is of economics. And another one is about awareness. And I'm going to talk about those and take them in turn. And when I talk about awareness, I'll talk particularly from a UK perspective. So in terms of economics, at Hefe, we did a simple thought experiment, and we figured out how much energy do you get from a typical US land well that costs maybe between $5 and $8 million to drill. And we came up with roughly how many barrels it was going to produce, roughly how many megawatt hours there were per barrel. And we thought over the course of a well, it's about 1,000 gigawatt hours that the well will produce. This is at source. This is before you get into efficiency of combustion and use and whatever, but this is the energy delivered. So if we drilled a similar cost well and maybe it delivered 8 megawatts and 90% utilization, so we have 10% allowance for maintenance or for shut-ins or whatever, then it takes it 16 years to produce the same amount of energy as the unconventional oil or gas well might produce in a few years, a handful of years. But it carries on producing afterwards. It might produce for another 16 years. It could produce for longer. And so in the long term, it looks like it's a good investment. And in terms of energy per dollar expended, it looks like it's a good deal. But it does imply that there's a need for patient capital. You're not going to get a rapid return on investment. And so that suggests that there is a role for people like pension funds, endowments, sovereign wealth funds, and also, dare I say it, for governments in driving this industry and getting it off the ground. Is it expensive? It's actually not that expensive. This is work done by Lazard showing the levelized cost of energy, which basically this is in US dollars per megawatt hour. And you could see that geothermal is not as cheap as solar or wind, but it actually looks like it's cheaper than nuclear. It's in the same range as coal. It's it doesn't. It's not an outlier on that chart when you look at it. And it's relatively new and it's relatively low scale. And when you look at what Lazard shows has happened to wind and solar, the levelized cost of electricity follows a very typical decline curve. You look at any new technology, you'd expect to see a curve something like this, where stuff starts off pretty expensive, but over the course of a decade, it significantly reduces in cost. And you can also overlay over that what happened with unconventional oil and gas in the US, where is if you look at new oil or new gas production per rig in the Permian Basin over the last decade, you can see on the curve on the left, the new production per rig is shown in brown. On the right, new gas production per rig is shown in blue. They both increased significantly, very significantly, if you look at that in percentage terms, in terms of barrels per day or cubic feet per day. And so that suggests that the oil and gas industry got much better at drilling these wells over the last decade. And the geothermal industry could do exactly the same in the same way. In terms of awareness now, I'm going to talk a little bit about what's happened in the UK, and I'm going to talk about there's a UK House of Commons committee that looked at technological innovations of climate change, and they asked for submissions. And I had a look through those submissions, and I pulled a lot of information out of those submissions in the course of putting this presentation together. And there were 34 submissions in total. There aren't 34 organizations listed here, but some of the organizations and individuals that made submissions are listed here. One thing that's notable is that the IMechE didn't make a submission. So either IMechE was not aware of this, or was not interested in it, or didn't have anywhere in its structure that was capable of talking about geothermal. But something that you think maybe IMechE should have been involved in, it wasn't. But a lot of other people were. And some of the messages that came through in terms of barriers, lack of market awareness, lack of public perception, difficulty of getting funding, lack of government support comes out in quite a few places. Lack of support and the risk of falling a long way behind its technological competitors, particularly the Europe, the USA, and China. And China's starting to look big in this. We've seen what China's done with solar power. We've seen what China's done with electric vehicles. The World Geothermal Congress was held in Beijing earlier this year. I didn't go, but I have colleagues that went, and they came back and they got the impression that China is going to go into geothermal in a big way, wants to become a global leader, and is prepared to spend money on it. And that's a dramatic contrast with where we are in the UK at the moment. Problems with resource permits. Who owns the heat? It's not entirely clear. And if we don't have a framework that identifies who owns the heat, then that could become an issue. Potential. UK geothermal industry with government support could be worth between 5 and 7 billion per annum by the end of this decade. By 2050, it could deliver 35,000 jobs across the UK supply chain, many of which will be located in levelling up and the red wall areas, the areas that were looking for support at the time of the last election. And towards the bottom of the slide here, you can see the possibility of transferring many of the jobs in the UK oil and gas workforce into geothermal was completely ignored by the government's 2016 UK workforce plan. And also, if you look in the submissions, you see there is tremendous amount of opportunity for the UK oil and gas industry. The UK is very strong in oil and gas technologies, and many of these technologies are directly applicable to geothermal. And I could spend the rest of the day telling you why that is, but I'm going to rely on other people's submissions instead. You see these submissions. I'm not going to read all of these out, but you see people like Seraphy Energy, REA, Angus Energy, Geothermal Engineering Limited, talking about how we've got in this country the capability and the skills to be able to transfer directly into geothermal heat extraction. You can see some more here. Skills and knowledge already present in the UK, but under threat as the oil and gas industry declines. So skills that we could lose if we don't act in the next few years. The requirement of government support to allow that diversification and that transition. And perhaps the most interesting one here came back. I talked earlier about the government's 2016 oil and gas workforce plan, ignored geothermal. Contrast that with China. Sinopec's Green Energy Geothermal Development Company was established in 2006 to transition oil and gas extraction expertise and business models into the geothermal industry. It claims its operations have already avoided 11 million tons of CO2. The point is, China was thinking about this in 2006, and we still haven't got to that point in the UK in 2023. So who's going to win this race? You know, I think the time is now for us to act and for us to take our experienced professionals and move them into an industry which is very, very suitable for their needs. So those are all the submissions to the committee. Where are we now? Well, if you look in the House of Lords library, you can find the latest and the greatest in terms of the government's position on geothermal energy. That House of Commons committee, unsurprisingly perhaps, expressed concerns that the government had been slow to exploit the potential of geothermal, not integrated it into its net zero strategy, and that this appears to be holding back the sector, which it said could transform the UK's capacity to meet climate goals, to use homegrown energy, and provide energy security, and to grow the economy. And Kieran Mullen, who's been a big proponent of geothermal energy, moved a debate in the House of Commons earlier this year, June 2023. But the government's response is, yeah, but it's risky, it's expensive, and it's not got much potential. So it looks like unless we do anything different, we're going to be gifting it to China. I'm going to finish with a quote from Guillermo Sierra. Guillermo works for Neighbors, which is an oil and gas drilling contractor that's very heavily investing in renewable energy. Disclaimer here is that they are an investor in Jefe, my company. But Guillermo's exactly right here. When he talks about geothermal in particular, he's saying this is not the time to compete. This is time to lead and time to build and time to create. And we have it within our ability to create a new industry, should we choose to, and to build this capability for ourselves and for future generations. And the time to compete with each other and the time to be fighting over funding and customers will come later. Right now, we should be creating the industry. And I think that's a great message to finish on. I'll finish this slide. I think there's a CPD certificate available for this presentation. Should you require one, please get in touch with Murat. And we look forward to any feedback. There's a feedback link here as well, so where you can feedback on this particular event. And at that point, I'm going to terminate the formal part of the presentation, and I will turn it over to questions for myself and the panel.
Robert Kulka, Fiona Sellers, and Demetriadis Klinethis. I probably didn't get that one quite right, but I'm sure he'll correct me on that as we go along. So if I can ask everyone again, if you can see, well, I guess either drop your questions in the chat. You'll see the button or the icon at the top of the screen on your Teams windows. So there's a chat icon, and there's also a Q&A. So I guess we'll monitor both, because I can see we've already got a question in the chat section. So please feel free to get your questions fired in. But I guess I can maybe kick things off, John. It seems like there's huge potential. You don't necessarily need to be sitting in a location where there's a lot of tectonic activity, because there's obviously technology out there now, and a lot of this technology is obviously, well, I would say quite conventional. And you look at the UK, I think sort of heat supply from geothermal is around about, what is it, not, well, less than 1%. And I think in Iceland that you talked to quite extensively about was, I think it's over 90% of their energy, like heat and power supply, is coming from geothermal. So I guess the question is, from me, why we're not doing more?
It's a great question, and obviously I wish we were doing more. Yeah, Iceland, special case, as you mentioned, where you have tectonic activity, you have very high thermal gradients, you've got a lot of heat very close to the surface, and you've also got fractured reservoirs which have hot water or multi-phase water and steam, and you can produce steam for power stations. But the point is that, you know, you can do it in different parts of the world. As you said, we're not restricted anymore to those tectonic areas. And as I said in the talk, the technologies that need to be used to do that, they broadly exist, and it's stuff that we've already got in our toolbox, with the possible exception of getting to higher and higher temperatures. So why hasn't it taken off all over the world? Why isn't it being done in the UK? I think the awareness issue is one. I think there's a lot of people who maybe aren't aware of the potential of geothermal going forward, and I think that's certainly an issue that is prevalent in, you know, at least parts of the UK and some of the organisations in the UK. But also there's economics, and on a levelized cost of energy basis, hydrothermal, geothermal energy competes fairly well with all the other power sources, but hydrothermal is only available in those areas where there is tectonic activity. If you do modeling at the moment for unconventional geothermal, which is the EGS and the AGS that I showed you earlier, you could see the potential to get to those levels. But most things when they start off are a little bit more expensive. And geothermal has to come down that same cost curve that wind and solar came down. And it's very clear that it can follow the same kind of track as unconventional oil and gas followed. You know, that some of the pictures I showed in the presentation earlier, I think the cost of drilling wells has come down at least 3 or 4-fold in the last decade or so, simply because the wells are drilled in a kind of cookie cutter SimOps kind of way, that, you know, all the wells are very similar to each other, and you learn a huge amount as you drill lots and lots of wells that are the same. And geothermal wells would look the same. They'd all be very similar to each other, whichever technique you use. And so the cost of drilling them would come down rapidly. It's just the industry needs to start. It needs to be seeded, and it needs to take those first steps so that those economies of scale come in and those cost reductions can come in. And then it will be very economically favorable compared with other techniques.
Yeah, no, excellent. And I guess I probably got one more question. I'm probably in the selfish, fortunate position that as sort of chairing the session, I can probably steal a march. But I guess, you know, one of another maybe question I would have is around, you know, it seems an ideal solution for sort of domestic heat opportunities. And I guess there's been trials or test cases looking at the use of hydrogen, and, you know, that in some eyes is quite, you know, there's very mixed views in that. And I know some of the panel might jump in on this, and I'll welcome them in to join the discussion on it. But I guess geothermal, to me, I don't know if it can use, you know, essentially some of that same infrastructure. And is it to me, it seems like it's potentially a safer solution and a more, you know, again, a more conventional or realistic solution compared to hydrogen for like domestic heating purposes. Would that be a fair assumption?
Yeah, I'd say so. I think I mean I look more at deep geothermal for power than I do at shallow geothermal for heating. So I'm not going to pretend to be an expert on shallow geothermal, but from what I can see, it's fairly widely used in parts of the world. It's very, very easy, low-hanging fruit in terms of being able to replace gas or hydrogen or whatever else for heating buildings, heating domestic buildings and industrial buildings. And it's also low-hanging fruit in terms of emissions reduction, because although we quite often focus on things like electricity generation, electric vehicles, sustainable fuels and stuff like that, huge amount of energy is used just to heat buildings and to keep our homes warm. And I think many of us have the opportunity, if the right conditions were in place, if the right financial conditions were in place, to be able to use ground source heating and the like to heat our buildings. And there's a bit of confusion, I know. There's a lot of people, you see a lot of stories on the internet about how I installed a heat pump and it never worked, or it never paid back, or it failed. I think there's a difference between air source and ground source. I think sort of ground source heating, where you're using heat from under the ground, has got a lot of promise for heating.
Yeah.
And untold, unused promise at the moment.
Yeah. Excellent. And I'll maybe bring Patrick. You maybe want to give your thoughts on that. Can I, just before you jump in, can I again encourage everyone to drop your questions into the chat or the Q&A. There is a question in there that I'll come to just after this. But Patrick, do you want to give your thoughts or what you think?
Yes, certainly. One question I've immediately got really concerns how renewable it is, because rock, as we generally know, isn't renowned for its high thermal conductivity. So as you're extracting heat from the rocks, how quickly does that get replenished from elsewhere in the earth, and what effect does that have on the productivity and energy you can pull out from the wells over time?
That's a good question, and yeah, you're right. I mean, rock doesn't have very good thermal conductivity, and I often joke with people that it's just as well it doesn't, because otherwise we'd all burn our feet whenever we went outside. Because as in terms of renewable at source, there is heat in the center of the earth which is continuously being generated by radioactive decay of elements, and so there's plenty of source. I mean, certainly in the perspective of our horizon of our civilization, whatever, you can almost think about it as being unbounded or unlimited. So in that sense, it's renewable. Thermal conductivity of rock can present challenges in using it, though. One of the issues is, and that there have been studies done on this, there's been papers written about this. You drill a well in hot rock, and you just start to run fluid through the well. You cool down the rock immediately adjacent to the well as you take heat from it. And so what you then need is for the heat that's naturally present around the well to cause heat to flow into the rock around the well. As you get closer to the well, the cross-sectional area for it to flow through gets smaller. You imagine it flowing through lots and lots of annular rings. Each of those annular rings is smaller than the previous one as you get closer to the well. And so the area for the heat to flow through gets smaller, and you potentially get a bit of a choke. And it's very analogous to issues that you often get in production of oil and gas wells. You get a kind of choking effect as you get closer to the well. There are various ways of dealing with that. They can involve EGS, which is the artificially stimulating the reservoir by fracturing. They can also involve drilling multiple wells. There's one technique which has been pioneered by a company called Icarus in the US, that's what they call the thermal soak method, where you drill a number of wells. I can't say how many, but it's a fairly small number of wells. And then you switch between them to produce from them. So maybe you produce from well number 1 for a number of hours, and then the rock around it begins to cool down. You shut that well in, you produce from well number 2 for a while, then you go to number 3, and by the time you've produced from number 3 for a requisite time, first one's warmed back up again, and so you could switch around between them. So it is an issue, but there are ways of engineering to avoid that, so you don't get long-term decline necessarily, and you can get steady state production of adequate amounts of power over sort of many years.
Excellent. Demetrius, here's your chance to correct me on my pronunciation of your name, but do you have anything to add? Demetrius got a background in drilling and completion, so I guess quite connected from the oil and gas side of things.
Yes, Clisthenes. I already have colleagues who have made the transition, and it is not a transition. You know, it's a back and forth. You know, because the techniques are the same. Of course, you know, we shouldn't underestimate the added complexity in some areas. For example, when you drill in high temperature environments, you need more expensive and more complicated tools. The equipment and the materials you use, they have to maintain their integrity at higher temperatures. It is difficult drilling in general. So you go through formations that are difficult to drill for many different reasons. So at this point, you can say that the cost is quite elevated, but with more scale comes also lower cost, as we showed before. This has happened before. So the manufacturers of the equipment are more or less the same at this point in time, but there is also, I think, a lot of potential for smaller companies to create a niche and to provide this kind of materials and tools at more competitive prices, and even dedicated rigs. We have seen that in Finland, where they have you know rig companies specializing in geothermal, and this it's already reducing the cost. Also, I have personal experience in Kenya, where we were drilling for hydrocarbons, but we had in an area where there was already a nascent geothermal industry, because the temperature gradient was high, and it was also volcanic formations, and that's how I know it is this overburden. For us, it was an overburden. Yeah. It's difficult drilling, so we should not underestimate that. We should not think that geothermal drilling is like something cheap and easy. It is not at this point.
Yeah, I guess. Yeah, sorry, John, go ahead.
Yeah, that's some very good points there, and yeah, I think I saw an article recently, and I can't remember what the number was, but Kenya has just announced a significant investment in its geothermal resources, which, as you say, they're blessed with a high geothermal gradient, and so it's relatively easy to do it there. The point about drilling different formations is a good one. As you get deeper and deeper into ultra hot rocks, there's a number of technologies on the horizon, any of which might be successful in drilling deep rocks at a high speed, including things like millimeter wave drilling and plasma drilling. And I'm going to upset somebody because I've missed out one of the techniques, but there's a few different kind of what you might have thought of about like science fiction almost techniques that are having money spent on them and invested in and being developed. But even if you look at just using sort of PDC bits like we use in the oil and gas industry, some of the work done at Utah Forge in the US, which is like an experimental drilling site to prove geothermal technologies over the last couple of years, has been outstanding. And you know, when I joined the industry, oil and gas industry, using PDC bits 30-something years ago, it was kind of unheard of to drill any formation at 100 feet an hour with the PDC bits in those days. And the ability to drill granite at 100 feet an hour with PDC bits at Utah Forge, which has now been proved, is quite eye-opening, and it's going to be a big help with the economics of doing these things. I know there are other problems other than just formation hardness, but the ability to drill those formations at such speeds is very, very encouraging.
Yeah. Fiona and Robert, I will give you an opportunity and bring you into the conversation just in a minute. But I guess just around that, and it's linked to one of the questions, I guess, here as well from Evan Ball Jones. But you know, I suppose for that to progress the use of geothermal in the UK, you know, if we're looking at that from the UK perspective, and to what you've both just been talking about here, I guess there needs to be some stimulus and incentive, you know, so basically the government needs to do more to, I guess, incorporate within the, you know, the strategy for energy, and also, you know, that stimulus coming from the finance as well, because you know, for small companies to be able to progress technology or innovate, you know, they need something to, I guess, ultimately take or develop that seed of thought. And the question in here is as well from Evan Ball Jones was around why are oil and gas not financing the technology development, as it means they can continue to employ their employees and move into another sector whilst maintaining regular income. And I think that's a really good point. It's, you know, so is it a case of industry and government working in partnership to, like I said, provide that stimulus? I guess, John, I would probably ask you that.
It's a good question, and the question is, why is the oil and gas industry not financing the technology development? And I think to an extent they are. You know, I mentioned in the presentation, one of Hefe's investors is Nabors Industries in Houston, which is one of the major oil and gas drilling contractors. And they've put money, I think, into 4 or 5 different geothermal startups at various stages, as well as other renewable energy investments. And they're not alone. And I think there's a lot of money that's coming from oil and gas into technology development. We'd like there to be more, obviously, but the industry is certainly stepping up, because I think a lot of the service companies in oil and gas can see that geothermal, it's just another market. You know, that you can make drill bits. You know, many of the bit manufacturers are actually providing bits now for geothermal wells. You can provide directional drilling services, or, you know, sort of well completion services, or, you know, casing, whatever, rigs. You could do that in geothermal wells just as easily as you can in oil and gas. But for a new technology to take off, you need a couple of things. You need the technology and the technical capabilities, but you also need the market and the needs. And I think, you know, that the oil and gas industry can do a lot in terms of developing the technology, but we also need to be drilling the wells, and we need to be planning to drill those wells. And I think there's clearly a role for industry and business there, and ultimately it's the market that's going to determine how many wells are going to be drilled. But I think there's maybe also a role for governments to kind of seed and stimulate the demand, and you know, give the industry a step up and kickstart it.
Yeah. I'll take let Demetrius in, and I'm conscious we've got a hard stop. 1 o'clock. So like I say, Rob and Fiona, I've not forgotten about you. You'll get your chance just after this. So
just a quick remark that the government, I think, first of all, we have a good regulator, you know, that other in oil and gas in the UK, that others other countries are looking as an example. One example that I have seen from Mozambique is that the government there is linking oil and hydrocarbon development, which is gas in Mozambique, with other technology development. So the license to operate of the operator is linked with participation in other renewable, you know, for instance, basically hydropower. I know Total is doing this, so they are linking. If they want a license, they link. So the same can happen here in the UK, for example. That if a company wants to have hydrocarbon development, they could mandate that they also need to have so much power, so much money invested in this case, geothermal.
I like that. That's an interesting idea. I like that.
Yeah, excellent. Right, Fiona, Robert, here's your chance. So, what's your thoughts on geothermal in terms of the potential for the UK, and do you think at the moment it's a missed opportunity?
I think I'll just chip in very quickly and say thanks, John, for that presentation. I definitely learned a lot there about the different techniques and so on. And I think I noticed there's quite a few questions in the chat in the Q&A function as well. Willie, we might want to pick 1 or 2 of those before we have to leave. But I just wanted to make a point that I think there's probably still a bit of resistance in the UK to geothermal in the public. And I'm wondering if there's anything in the sort of education and awareness that we could be doing, or maybe we could be copying some of the education and awareness that other countries have done that have successfully implemented more geothermal projects, and if there's anything we can learn there.
Yeah, I'm just going to say apologies because I've missed the I'm not getting the questions through on the Q&A.
Okay.
Please, so apologies if I've not had a chance to answer your questions. And what we'll maybe try and do is, you know, if we can get the questions, we maybe can do something afterwards to kind of pull something together to try and, like I said, help answer some of these questions.
Sure. Can I just jump in on Robert's point? And it was remiss of me, I should have mentioned it in the presentation. In terms of awareness and education, there is an organization called Project Inner Space, which is a non-profit. And in full disclosure, I do a little bit of work for Project Inner Space. But that Inner Space's remit is kind of multifaceted. But it is, at least part of it is to promote awareness of what's happening and the opportunities for geothermal energy. If you look on their website, which is projectinnerspace.org, the inner space as opposed to outer space, they have an annual event called Pivot, which is looking at how oil and gas technology can pivot into geothermal. And there's, I think, 3 years now of resources from what is typically sort of maybe 5 days per year of panel sessions and conversations. And so there's a lot of material there, if anybody's interested, that you could delve into. And it's all available for free.
Excellent. And I'll bring you in there, Fiona, just quickly. There is one of the questions I do see here in the chat section, which was on, you know, do the geothermal installations pose any new environmental risks? So I guess, you know, you did touch on the fracking aspect before, but I don't know, any thoughts, Fiona, from you on geothermal, the potentials and even the environmental aspects?
I was probably more back to the materials that we were kind of discussing there. So are the materials available within from oil and gas or within geothermal to cope with the high temperatures, or is it more extreme that needs to be developed?
That's a good question. And you know, the biggest challenge, certainly for my area, is looking at drilling equipment. And the biggest challenge there in terms of materials is sensors and electronics. And the materials that you use for, you know, structural materials like steels, their properties do decline with temperature, but that's fairly well known, and you can model it, and you can just use the same techniques as you use to design a piece of equipment. You just make different assumptions about material properties and material strength and stuff like that. With sensors and electronics in particular, the oil and gas industry did a brilliant job over the last few decades of moving temperature capability of electronics from 120 Celsius to maybe 150, and then maybe 170 or 175, and in a couple of kind of rare but notable cases up to 200 degrees Celsius. But almost all of that work was done by basically taking existing commercially available off-the-shelf equipment and selecting, so screening and selecting. So you'd buy some components, you'd heat them up above their specified temperature, and you'd see if they survived or not. And if they look good, maybe you buy 100 of them or 1,000 of them and heat them up, and maybe a fraction of those would survive. And you take the hardened ones, you know, the survivors, and then you'd use those in your equipment. And if you pardon the pun, that approach runs out of steam at around 200 Celsius. You just can't go any further. But luckily, oil and gas is not the only industry that requires high temperature equipment. Aerospace and space both have extremes of temperature to deal with. And if you look outside of oil and gas, you could see techniques for building components and managing temperature, which you know, we can import and go forward with. So yeah, there are some very extreme materials challenges, and HEFE set up to try and solve some of those challenges. They're not simple, but they are kind of doable. But yeah, I mean, any material you think of, you're pushing the limits as you get into the 200, 300 Celsius range.
Fantastic, John. And I think at that we'll wrap up at that. I'm conscious that you need to be away, so I guess that just leaves me to say a huge thank you to you for pulling together a fantastically informative presentation. Also, a big thanks to the panel and also everyone that joined us. Like John noted at the end of his presentation, there's the CPD credits that you can get from the session or for the session. So make sure that you all do that. I guess this wraps up our series of presentations or sessions, webinar sessions for 2023, and there'll be, I guess, announcements early in 2024 on what we're doing next year. So I guess without further ado, just wish everyone a safe and Merry Christmas and Happy New Year when it comes. Enjoy your break, make the most of it, and we'll hopefully see you all back here in the new year. Thanks very much just now.
Thanks, everyone.